Hi students, now we will discuss about Gauss's law for the magnetism. You are aware about so many properties of electric fields, Gauss's law. So I am just using that is called as our Gauss's law for magnetism. You are very well aware about Gauss's law for the electric field. Same is the property for Gauss's law for the magnetic field. You are first of all we are doing just some quick revision of electric fields Gauss's law. You are aware about such type of property. You are saying that integration of E dot dA is equals to sigma q by epsilon 0. Its another name is called as our electric flux. You are seeing that let's say we have such type of undefined area, and let's say I'm just naming it as a small segment of ds, and electric field lines are passing through it in a such a fashion. So same is the course for electric field lines are coming outside. So we were using that whenever we have such type of a closed loop. It's electric field lines are entering into the closed area or surface, and that is called as the integral part of E dot dA is equals to, or you can say directly proportional to the sum of the charges and inversely proportional to the permittivity of the vacuum. Same is the course. Now we will apply such type of law for our another property, very good property, that is called as our electric field, and after that now we will have another part that is called as a magnetic field. Same course, let's say first of all I am putting that integration of E dot dA or ds is equals to sigma q divided by epsilon 0. You are very well now aware that the properties of E and or a relationship between the E and B is not something different. That is called as an replacement of E with B, and this is the same course. You can just say that a dA, or you can place that a ds as well. Let's say be careful, this is not the vector because our area is not vector, but yes, it is representing some of the positions. Here we are saying that that is sum of the all these charges, and this is the property of electric field lines, because in electric field you can say that sigma q is responsible for the production of electric field. But if we will discuss about magnetic fields property, that there would be the requirement of current. So what you will say is that instead of sigma q we will place that I. There is another representation of 1 upon epsilon 0, and that is called as a mu 0. That is called as you are very much aware about, that is called as a permeability of vacuum. And later part in electromagnetic waves, EM waves, you will learn that it is also containing some of the constant, that is called as our permittivity of vacuum. So whenever you have such type of relationship, you can compare this one with another part. So we can have this is mu 0. So this is how that is called as a representation of electric field and magnetic fields formula. So now we will just come to the conclusion that let's say we have a such type of undefined area. Let's say I'm just naming this area as a dA area or ds area, and it is placed in the sum of the component, let's say x or y coordinate system, and my magnetic field lines are entering into the area. So let's say magnetic field lines are going to come outside. These are my magnetic field lines. Yes, it is a vector part. So we can say that the number of magnetic field lines entering into the closed area, same will be applied to the electric field area. So you can say that it is called as a summation part. So I am putting integral part, and it is a closed loop. So this is called as a closed integration, and it is called as a dot product. So this is my magnetic fields formula. It is called as a B dot dA. So net magnetic field lines entering into the closed area will be coming out. Again, you can say that number of field lines going to enter into the area, same number of field lines coming outside of this area. The conditions are that here we will just use another notation, that importance part is that our angle between the n cap. This n cap is nothing. This n cap is a representation of angle where our magnetic field lines and areas are placed. Let's say I'm just giving you another example. I'm drawing one line segment, and into the line segment you can say that let's say I have such type of one line segment, and let's say x and y coordinate I am placing like that. This is my x and y coordinate, and into the x and y coordinate I am putting my area. Let's say it is having some area. Let's say length is L, and let's say height is also L. So this is the square. If I am entering my magnetic field lines into this area, let's say my plane is in the x and y direction, so my magnetic field lines are also parallel to it. So these are my magnetic field lines. So you can say that if my magnetic field and my area both are in the same direction, let's say this is in the I cap, this is also in the I cap, so I can simply represent it that if both are parallel, then and then my magnetic field lines will come out or pass through it. This is also a representation of our flux as well. So I'm putting first of all our formula that we have integration b dot dA or ds. So I'm putting that if it is a b dot dA, you are aware about so many properties of a dot product, then I am opening this bracket and putting that the dot has been removed, so we can have a b dA cos theta. As you are aware that we have a notation that a dot b is equals to magnitude of a and magnitude of b of cos theta. So this is how you can represent it. So now this is the representation. Now integration of dA is nothing. Integration dA is called as our area, or you can say that if you are putting that integration of ds is called as your surface. Yes, in examples you will just place that our area is called as the L square, because my length and breadth of this square is called as the L. So my flux phi is called as a b, area is a, and that is called as a cos theta. So this is my flux formula. Yes, we will place some of the component, and you can place that yes, its property suggesting us that is called as a mu 0 of I. So what I am doing is over here is that I am putting, it's a simple case is flux phi is equals to ba cos theta or bs cos theta as a surface, or a is also surface there, where your b is called as magnetic field. So I have different type of cases. Let's say my theta, first of all my theta is called as a 0, another theta that is called as a 90 degrees, and theta is equals to 180, or you can say that pi or pi by 2. If I am saying that theta equals to 0, it means that my magnetic field, let's say that is called as a b, and my area dA both are in the same direction, either I, then this area must be in the I, or either j and it is also in the j. Same is the course. So you can say that my flux phi is equals to ba. So this flux is called as a maximum flux. Let's say my theta equals to pi by 2, so you can say that cos pi by 2 is called as a 0, then that is called as a flux phi is 0. So you can say that whenever your magnetic field and area both are perpendicular, then your area is perpendicular, automatically your flux becomes 0. So no magnetic field will come, or magnetic field lines will come out, or flux will be 0. There are another properties that you can also say that magnetic field lines cannot enter into this region. So magnetic field lines are not entering, that is why also you can say that, let's say my net, you can say that unit vector that is in upward direction, and my magnetic field lines are trying to enter into this region, there are no chances of Gauss's law. That is a, you can say not availability of entering region, that is why you can say flux phi is 0. So this is how you can represent it. Now my theta equals to pi, my theta equals to pi, so you can say that my flux phi is equals to minus ba, as you are knowing that cos pi is equals to minus 1. So it means that my magnetic field lines, let's say this is my area, my magnetic field lines are opposite to this region of opening part of my area. This is how you can represent it with the help of notation of a flux. Now one more good property and unit of this flux I want to represent in front of you is that that flux phi, let's say ba cos theta. or if I am just taking ideal condition that theta is equals to 0, when you can say that the maximum flux phi will occur, so I can just say that it is BA. You are aware about the units of magnetic field and the area. Magnetic field is containing that unit Tesla, and area is called as a meter square. So my very first unit is called as a Tesla meter square. Another good unit of it is called as a Weber. Yes, you are aware about so many other properties. Wherever you will learn that magnetic flux, you will also found out that unit is mentioned in the terms of a Weber. Yes, and the fluid mechanics also you can just use such type of units. So you can say that our unit is called as a Weber or Tesla meter square. A very well used unit is called as a Weber, because wherever you will just find it out examples or its measurement, you will find it out such type of word. Another unit I want to mention is called as a dimensional configuration of it. It's a containing dimensional configuration is called as a M1, L2, T minus 2 and A minus 1. This is how you can represent your magnetic field and area. It's a combination. You can say it's a dot product is called as a flux phi. So you can say that net flux, as per our Gauss's law, net flux phi is always 0. So in other word, if I want to represent it, I can say that integration of B dot dA is equals to sum of mu 0 I. Yes, instead of mu 0, or you can say permeability of vacuum, you can use material as well. So you can say that mu I, because of the material. I want to also mention or highlight one more thing, that you are aware about the property mu by mu 0 is called as a mu r, that is called as a relative permeability, which is called as a unitless quantity. So my formula, you can use this notation as well. B dot dA is equals to sigma of current I, but yes, mu or mu 0 is replaced by, in the other terms you can say that it is mu 0 and mu r instead of a mu. So this is how there are different type of categories, different type of formulas, you can utilize it and prove that it's units and dimensional configurations and magnetic field properties. Yes, those properties which you have applied in the terms of electric field, same properties you will apply over here for the magnetic field as well. It means that this is purely control C control V. It means called as a copy and paste of your Gauss's law for the electric field properties or electric field. Same is the course, same are the chances, only the change will be this one. Very first one is that in that electric part we were placing that instead of B, we are putting that E, and instead of a mu 0 and epsilon 0, we were representing in the terms of let's say these are the replacement 1 upon epsilon 0, and these are the changes. So you can remember this property, you can prove it's for the Gauss's law in so many school exams. For the 2 marks they are asking such type of examples. Now from this example I want to mention in front of you so many beautiful properties of example, or you can say that solved example of your textbook, where you have been mentioned so many theories, and you have to say that whether they are following Ampere's circuital law, magnetic fields property, or Gauss's law. So in front of you, let's say this is the very first figure. So in this first figure you can say that yes, it is shown that these arrows are indicating magnetic field lines, but you are aware that for the magnetic field it always follows such type of course. Let's say you can have a current carrying wire, and around that you can have a magnetic field produced like that, or you can say that this would be the direction of magnetic field lines. But you cannot say that there would be a point source in the magnetic field. So here there would be a point source. So this figure is not fulfilling that properties of magnetic field, only because of the 2 reasons. Very first reason is that there would be a point source, which is not possible in magnetic field. And another thing is that magnetic field lines are emanating from source. It must be entering and coming out from some area, so it is not fulfilling the property of our Ampere or either Gauss's law. So these 2 properties are not fulfilled. That is why you can say that very first figure is not satisfying our condition, so it is not true so in the comparison with magnetic field. Next figure in front of you is that here these arrows are indicating different magnetic field. You can say that our magnetic field lines are always parallel, likewise our electric field lines, but yes, they are not supposed to be intersecting. Here these points are showing that our magnetic field lines are intersecting, so magnetic field lines never intersect. So as per that point of view, it is not showing that. Another property is that it is showing that closed loop. Likewise our electric field lines, yes, you are aware about the dipole as well, magnetic dipole and electric dipole. In magnetic and electric dipole moment, you can say that they are forming closed loop, but normal magnetic field lines doesn't form such type of a closed loop. So here they have shown that closed loops, so you can say that it is not true so as per your magnetic fields property, it is not true so these two figures are completely disobeying our characteristics of magnetic field, so you cannot say that they are true. Next figure is that it is in front of you is that figure of a toroid. In toroid, you are aware that when at different points we have different type of magnetic field inside surface and outside. So you can see that magnetic field lines are forming such type of a closed loops. They are fulfilling the properties of magnetic field lines and not intersecting. So in the toroid, they are following our very first property is called as Ampere's circuital law, and they are also following that properties of magnetic field. So this figure is completely obeying our properties of magnetic field and magnetism, so we will say that it is completely true. So next figure is called as our solenoid. In solenoid, yes, magnetic field lines are represented, but as per our rule they are entering and the same amount of magnetic field lines are coming outside, but they are not completely, you can say, linear. There must be some perpendicular part, or there must be some band, because you are aware that magnetic field lines are always experiencing, or you can say electrons are experiencing such type of curve, same type of curve you can observe, it is not linear. So this is not shown in this figure, that is why you can say that it is not fulfilling the condition of magnetic field lines. Next in front of you is shown that our magnetic field lines indicating that it is entering over here and coming outside. As per our magnetic field lines property, I am assuming that this is a bar magnet. My magnetic field lines are going in this direction, so it is inside, it is starting from S and ending at point N, and from the outside it is again coming back to the S, so it is fulfilling the condition of magnetic field lines, or you can say it is look like a bar magnet. So it is fulfilling all properties of magnetic field lines, so it is true. So in the next figure you can say that there are three different points I am just mentioning over here. That is this is the point 1, this is the midpoint 2, and another point 3. You can say that at point 1 and 2 they are fulfilling the condition, likewise our bar magnet, but it is inside, you can say that these are the magnetic fields direction. It is opposite to our Ampere's circuital law property, or it is not fulfilling the bar magnet's magnetic field lines property. So this figure is not fulfilling, that is why magnetic field for this figure is not true. So this figure is wrong one. Next is that in this figure you have been given that such type of a closed loop or square loop, where you can focus over here. You have magnetic field lines passing from the N region to S region. Yes, again it is also like that. You can see that in a solenoid we have mentioned it is a straight line, not intersecting parallel to each other, but at the same time it is not bent as well. So you can experience that whenever magnetic field lines are passing from N to S, there must be some bend, so it is not fulfilling the properties of magnetic field or magnetism, so it is also not true. So you can see that there are different type of examples in front of you. You can say that here it is fulfilling the condition or not. It has been defined by its property of a magnetic field or point source, or they are intersecting or closed loop. So it is ideal way to recollect all your properties of magnetic fields knowledge whenever you will solve such type of examples.